Hello, everybody. Very happy to be here. Thanks for coming to my talk. My name is Michal. I work at Akka Technology, and I want to introduce you to the world of scalable web services. And I must warn you, this will be a very technical kind of session. I hope you're okay with that. There will be 4 scheduled slots for asking questions, like 1 minute or so. Please use them. And let's begin. What's inside? What's there for you? We'll make a web service from scratch. We'll use actor model for that, Akka and Scala, and I will do some tutorials about those technologies. Then we'll try to test the performance, the throughput of the web service. We'll use Unix tools, open Unix tools, and we'll try to see whether we can improve the characteristics of the web service we created in the next session, in the last section of the session. Okay, Akka. Who knows Akka? Knows means knows what it is or does something with the technology. Okay, for all the others, here's a 1-slide Akka tutorial, and it's really 1 slide. So you can, whenever you hear about actor, you can just imagine that this is just a piece of code that can be run just on 1 thread at a time. So you can put many variables or mutable state inside the actor, and you don't worry about it being accessed concurrently. So this is the first thing, lightweight, very lightweight thread. The second thing, and the third one, is the way we can communicate in actor model. So the exclamation mark, we call it tell. You can just send a message to the actor, a command or another message. You just fire and forget. Send the message and don't want anything back during this call. So this is exclamation mark tell, and ask is a question. So you receive a future after you call ask for the actor, and in the future you will receive a response from this actor because you want that. And actors have mailboxes. So you can send many messages to one actor, but as I said before, it's just 1 thread, so it will process the messages in the order that they are received. So it just gets messages from the mailbox after it processes the last one. And the most important thing for some people, it's creating children. So just like in real life, whenever actor creates a child, it's responsible for that child, right? So whenever your child throws an exception, you need to take care of the exception and maybe create another actor child, or do something different. Things like that. So this is called, in Erlang and other actor models, this is called a supervision strategy. You just provide some code that will be executed whenever something goes wrong. Any questions about Akka? Because this is it. Okay, 1-slide Scala tutorial then. The code on the left is Java code for a simple Pojo class, right? So it's junction, and it has just 1 field, ID, and you just have a constructor and get ID, maybe some setters, probably, but I don't want any setters, so I don't have them here. Hash code, equals, copy, those kinds of methods which didn't fit on the slide, so I just commented them out. The same exactly thing can be done in Scala using the case class notation that you can see on the right. So it really, under the hood, it generates all those things. This is the first thing, and the second one about Scala is pattern matching, which is the bottom right part of the slide. So you can match on messages, and whenever message is, for example, a type of junction, the code in this case, the first case, will get executed. And if it's some other type, this part of code is being executed. So this is some kind of instance of, but a nicer one. Any questions about Scala? Cool. I promised you that we'll implement a web service from scratch. And I mean it. This is the example that we'll be using. So imagine there is a containers going in your warehouse. And you have several scanners on the way, like here, the left red arrow. There's a scanner. And each time the scanner scans the container, it sends a request to our HTTP server, which we'll implement, with the container ID and the junction ID on which this particular scanner is. And then the web server we need to create needs to return the decision for this particular container. For example, should it go forward or should it turn right? And as you imagine, this needs to be nicely timed, right? So this has some boundaries on upper boundaries on time. And yeah, this is the example that I want to implement. Any questions about the example? Just raise your hand or shout. Technically speaking, what it looks like. Just a standard web server, junctions is a path, then we get junction ID and decision for the container and the container ID. So just 2 parameters in this nice web service, and it returns a JSON with the target conveyor. This is the decision that our service made. And the assumptions, just for the sake of the presentation, I don't really care about the business logic. It's a function that we'll call, and it always does a good thing. We'll just focus on performance. And the function that makes this decision takes like 5 to 10 millis to execute. Okay, let's code it. Can you see the screen? Yeah, okay, class. First, we'll implement the REST interface, actor. So everything will be modeled as actors. Extends actor. Each actor always needs to have a method which is called receive. So each actor has a method receive, and the messages that are coming towards this actor need to go through this receive method. And this receive method usually has some code, but for the REST interface one, we'll just use a helper method called runRoute, and the route will provide. So this actor is an HTTP service-based actor. This HTTP service base provides the runRoute helper that generates our receive method. And the best part here is that we can define our route with a very nice DSL. So let's make a path. So we said it was junctions, then we want some int number as junction ID, right? Number. Then we need to have decision for container and another int number. So this is a path. What it does, each message, each HTTP request that gets sent to our server is modeled as message and is sent to our actor. Then it goes through the directives in our route. So the first directive it meets is path directive, right? So what this path directive does, it just checks whether the HTTP request has been sent to the right endpoint. In this case, we want it to be sent to junctions / some int number / decision for container / some other int number, okay? And if it does, it goes inside our block of code here. If it doesn't, it just gets rejected. So we get 2 int numbers, which are parameters, and let's just name them here, junction ID and container ID. Those are variables that will be available inside our code. Then we give another directive. Again, when the message meets the path criteria, then it also needs to meet get criteria to go inwards. So get means that this request needs to be of HTTP method get. And then when we know exactly that those two criteria are met, we just complete the whole request with some kind of response. what we can do here is we can log something. Log info, for example, we don't have log there, but we can add another trait, logging actor logging, and this will automatically give us log here. Request, and just so that we know that requests are there. A request for junction ID and container ID. Okay. Then we just call our business logic function. Decisions. Where should the container go? Junction. It needs junction and container. We don't have them yet, so we just create our domain objects. Container is just a case class container ID, and junction is junction. I will just finish that and show you the implementation of those two messages. So this is our two domain objects, case classes, as I showed you before, and those are just IDs for now. We don't need anything more for this demonstration. And what we do next is we just return the result from our web service. And the result is Go. It's another case class. What it takes, it's just takes the decision. So it's implemented like that. Case class Go, but there are 3 more lines here. Those what those 3 lines do, they are, we can just make sure that Go is serializable to JSON and out of deserializable from JSON. So this one line here does just that. So we know how to transform our case class into JSON. Because this is our response, Go. And basically this is the actor that takes care of all HTTP stuff. Let's create the application here, single noded application. Let's create this system, actor system. First, if you want to create actors, you need to have a system. All the actors reside inside the actor system. There's no way around that. Let's call it sorter, and then system actor of creates the actor. Let's REST interface. Okay. What we miss here is we didn't provide any port, so let's call it 8080, but we don't have it here. Exposed port. So we are creating a parameter exposed port, which is an int, and we know now that we need to bind to this port, right? So our actor, in order to serve the messages, to serve the service, need to bind to the interface and port, and we can do something like that. First, we need to pass the system from the actor. It's not so important right now, but this line is important. So we just go to the IO extension and send the message to the IO actor to bind ourselves to the interface, which is 00000, and port, which is exposed port, which we got from the caller, the one who constructed us. This should all compile, I hope. And let's see whether it works. Yeah, so we see it bound to 8080, and let's check whether it works. I have a curl here. Yeah, so we can see the target conveyor decision was made. It works fine. Let's go to the slides and see what we did. So this is the first step. We created a web service from scratch. The REST interface is an actor, and it just gets all the HTTP requests as messages. As you know, all those messages are being processed in sequence, so one after another. And what kind of throughput do we get? in terms, okay, let's guessing game for you guys. So low or high? Who votes for low? And who votes for high? It depends, right? We probably will get something when we test it. And how to test it? We'll try to do 5 junctions in parallel, and each of the junction will get 2,000 requests, and all of them will be in parallel. Okay, so in total there will be 10,000 requests. Then this bash command at the bottom is exactly what we see at the top. So what it does, it just sends 2,000 requests in parallel to those 5 endpoints. Okay, this is what I use. We use GNU parallel to parallelize the requests being sent, and the Apache bench in order to make them being called one after another with some features like keep alive. And just a warning for you, don't do benchmarks or other throughput testing on your laptops. I will do that anyway. What I did in order for the test results to be meaningful is that I capped Akka. So it's a very performant library. And what I did, I just made Akka use just 2 threads out of 4 or physical 4 or hyper-threaded 8 on my computer. That's how we can measure some meaningful results out of it. So remember, this is just capped Akka. So let's test it. Let's test it. Here's the application is running, and the code itself. Sorry. Yeah, so this is what was on the slide, and let's go. As you see, the log messages are coming in, so that means the command is working, and this is the first slot for questions. Any questions? It will be about a minute for the test to execute. So this is the time for you to ask questions. Everything's clear. So once again, we have just one actor, which is REST interface. It just gets messages which are passed through path get to complete one message at a time, because it's receive method of this one actor. And we have just one actor in the system. And yeah, nothing more for now. The test should be wrapping up. And let's see how many requests per second do we get. So as you see, for each of the URL, we got around 34 requests per second. So this is our baseline to measure how we go. This is probably the lowest possible throughput we can get from this kind of application. Let's continue. How do we make it better? In actor model, whenever we have problems, we just add another layer of abstraction. This time, it's just adding another actor. So what we want to do is we just leave all the responsibility of handling HTTP requests to REST interface actor, and we just create another actor, sorting decider, which will be a business logic actor, so to speak. Okay? And what do you feel? How do you feel about this solution? I'll just quickly implement it, and please think about what kind of result will we get from our tests. Remember, it was 34 requests per second, and how many will we get now? So we just create another actor, as I told you before. It will be called sorting decider, extends, actor. What kind of method we need to implement? Receive? right? This time it will be a proper receive. We're using pattern matching. And where should the container go? This kind of message. And junction container. It's not yet created. Let's do that. Create case class in this file, junction container. We'll just move this message to messages here. So all our messages, all our APIs in the same place. And then let's implement the logic here. What we need to do is just move some of those things here, because this is our business logic. Decision and go. This is an actor, so we cannot just return. In Scala, we have implicit return. So the last statement in the block of code is the return statement. That's why this return here worked. So again, what we need to do in the actor, whenever actor cannot return anything inside his receive clause, we are sending messages here. So we need to send the go message to the sender of the message in order to respond. And in our REST interface, what we need to do is we need to ask our new sorting decider actor for the business logic or for the business decision that it needs to make. And this actor will be provided from the outside. So we just add another thing to the constructor. And here we can just ask the decider where should the container go. Okay. Let's rename it. It looks better. Where should the container go? And the container needs junction and container. Then we will wait, because we're just sending a message to actor. It can respond. It may not respond. So we need to provide a timeout. So let's have 5 seconds. Let's wait at most 5 seconds, and then map this message. So what we expect is to receive a go message in response to where should the container go, and that's all we need to do here. Does it compile? Who pays attention? What we did here in the constructor, we added a new parameter, right? So it won't compile because we need to provide it here. So in order to provide it, we need to create another actor, name it system actor of props sorting decider. It doesn't have any parameters, so this should just work. Let's try it. So this is the whole implementation. What we did, we just added another layer of abstraction, another actor, but we just moved the code around. It works. I'm running the tests again, going back to slides. Hopefully. Where are my slides? Here. Yeah. So this is what we did. We just moved the business logic from REST interface into sorting decider. So how do you feel about that? We were waiting, so there's a second slot. Any questions? If there are no questions, then let's begin our guessing game. How many requests per second do we get with this solution? Who knows? Who knows? Sorry? Hundreds. Why? Okay, there's a mic here.
Well, I hope it's non-blocking, and the first call will finish, and the future will be returned, and when calculation is done, it will propagate response. In that time, REST service will be able to process another request.
You are right only in a part of your description. As you see, we got the same results. Why? Because what we did here, we have, let's go through the diagram. Each message is modeled as, each HTTP request is modeled as message. And this is just one actor, one instance of an actor. So it gets created here, it's passed here, and you're right. There is future there asking, and it will finish faster than the business logic. But here, there's still just one actor, and it gets the messages with the questions, and it still needs to process them in sequence because it's just one actor. So we just moved the bottleneck downwards, but it's the same bottleneck. That's why we get the same results, okay? Okay. So a third step, let's really improve the performance. We introduce another layer of abstraction, of course, another actor. This time it's decider's guardian. We won't touch sorting decider. This is our business logic actor. We'll use it the way it's defined right now, but we will create another actor which is called decider's guardian, and it will create children. For each junction, there will be one sorting decider. So we'll be scaling based on junctions. Well, let's do it. Decider's guardian. So class, you should know it by heart right now. And decider's guardian extends. What does it extend? An actor. And what we need to implement? Receive. And yeah, there is a message going in the same message, but we want to extract junction out of it. And what we do, first let's create a name for our child. This will be J junction ID. So J1, J2, J3, this is the name of the actor, which we'll use to reference them. Junction ID. Then what we do is we create our worker, our child, our worker actor. First, we check whether it's already there. Maybe it's already created by using the name. What child method or function returns is an option, right? So if it's an option, then we can get it. But if there's nothing there, it's none, then we just create our sorting decider actor and give it a name that we just defined. What we do then is just forward the message to the worker actor, and we are done, really. What we need to change here is we don't want to use sorting decider as our main entrance to business logic, but we want to use decider's guardian. Okay? Okay, it compiled. Let's run the test. Waiting. Any questions? So what I did is just added a new layer of abstraction, decider's guardian. Any questions about decider's guardian? Ten seconds, and then we'll move to guessing game again. No questions. Okay, then tell me, what do you think the request per second will be? The characteristic? Higher. Who says it will be still the same? 1, 2, 3, 4, 5, 6, 7, 8. And who thinks it will be higher? Probably, maybe the same amount of people. But okay, let's check it then. It's higher. It's almost twice as high as the last one. Why is that only twice as fast as the previous one? Because Sorry? Can you wait for Mike? I can't hear anything.
As I remember, you are using 2 threads in your test.
Right. So the Akka is capped to just for 2 threads. That's Akka will use any threads possible. I just gave it 2. That's why we got the performance boost of 2 times. Okay. So we have non-blocking solution, which is concurrent. It scales up because whenever we add new cores, many more threads will be created at once, and we can use that in Akka. What about scaling out? What about if we don't want to buy new machines or new cores? We just want to add a new machine, which is the same characteristic of performance as the previous one. Does that work, in your opinion? Traditionally, in Java, like we had JBoss application, and we had application deployed on JBoss, and then when we wanted to scale it out, we just add another JBoss and cluster them together, right? This is called manual scaling out. Why is it manual? Because you have exactly the same application run twice. What you need to have is some kind of load balancer on top of it, which just balances the traffic. And it also needs to be very intelligent. In our case, for example, if we want to do something like that, sorting decider that's decides only for junction 3 and 1 and 2 needs to be on the left node, and 4, 5, and 6 on the right node. So this is the thing that we need to implement inside our load balancer, right? Based on the messages that HTTP requests that come in, it needs to decide whether to forward it to right or left node. And the second problem we have with the manual scaling out solution is that whenever right node dies, what happens? We just have functionality for 1, 2, and 3, but we don't have functionality for 4, 5, and 6. Even though we have the business logic here, right? So we could just move it, but this doesn't work like that. We need to do it manually. Enter sharding. So this is what this gives us. Sharding is a cluster extension for Akka. And as you see, those images are very similar. We just remove decider's guardian. So this is the actor which we'll get rid of. Because Akka is giving us shard region actor, which does exactly the same and more, because it does the balancing, the logical IDs between nodes, and many more things like that. So what we have here is we have an intelligent actor which can move messages between the nodes without the developer knowing about that. How does it do it? It uses this HM hashing function, which we provide. This is the only thing we need to provide. Each message that goes inside here is just passed through that function, and this function returns on which node this message should be processed. So this function is exactly the same on each of the node, right? And then it's passed to the right node, and there's a second hashing function which just selects, based on the message, selects the right actor for processing. Let's implement that. We'll just copy that, move to the sharded. Sharded up. And yeah, there will be a different kind of configuration. I call it sharded. So this is just ports, names, things like that. I will show you how it's being used right now. So config is just in Akka, sharded conf looks like that. So for example, we defined that the port is 2551 and the cluster name is sorter cluster, right? And we can just use it in our code. Get string, this is the name of the system, clustering cluster name, And what we do next is we create our shard region, our sharding. So cluster sharding inside the system is started. And here we need to provide 5 parameters. But I don't want to do it inside our application. Let's do it inside the file where the actor, sharded actor, is really defined. So let's create an object called sorting decider. Let's name it. First name will be sorting decider. We'll use those values that I'm defining right now inside the start sharding function in the app. Props, so this is the factory that we use in order to create the actor. Just props sorting decider that we had before. And those 2 hashing functions. So this is the crucial moment here. I'm defining the 2 hashing function right here. First, extract shard ID. So the first function, message goes into the system, and then we need to know which kind of shard ID it is. And Akka knows where this particular shard ID is being kept, on which node, on which JVM, which are dynamically created. Shard ID, this is of type extract shard ID. It's of course where should the container go. We just extract junction because we make decision about the shard ID based solely on junction. We return junction ID. For demonstration purposes, I will have just 2 shards, and that's all. This is the first hashing function. It selects the shard ID on which this particular message, where should the container go, should be processed. And the second function, extract entity ID, is called when the message is on the right node, but this function selects the right entity, which means the sorting decider in this case. And here we need to define junction ID to string, which just selects the right thing. It's just like a name of our child before, and the message itself, which need to be propagated. That's all, and we just use those things here. Name will be sorting decider name. Entity props will be sorting decider props. And we need to have some default settings. I don't care for now what they are. And those 2 hashing functions are the last parameters. Extract shard ID is sorting decider extract shard ID, and extract entity ID. And type name. Yeah. So we created, in the current cluster, we created a sharding extension. And then what we do, let's see the single node application. Let's copy this here. We create the REST interface actor, the same as before, but we do, instead of 8080, because we'll have different ports, because for each node, we'll need to have a REST interface. So this should be retrieved from the config. Get int application exposed port, I think. I will check it right now. Application exposed port here. Yeah. What we don't have yet is this decider thing. As we know, we need to use sharding actor, and there is a sharding region, which is just shard region, which we call by a string name here, and that's all we need. Now we'll just run 2 JVMs, one on the default port and one on the custom port. They will connect with each other automatically. Oh, sorry, this is not the right thing. Extract, I need to import that. Shard it up. It compiles. Yeah, so you see the many more things going on here because it's a sharded application. I'll just kill it and run it twice here so that you can see what's happening. I will use java -jar. So on top one is the first JVM, and this is the second JVM. As you see, though, they connected perfectly fine. I'll just test whether it works, whether we get the response, and then just run the test. 2 JVMs. Okay, sneak peek. We are waiting for the results, and now, if there are now no questions, any questions? Then the guessing game begins again. What will we have, in your opinion? What kind of performance boost? We have 2 JVMs. We scaled it 4 times. 4 times. Who says it will be less than 4 times? And who says it will be sorry about that. Higher than 4 times. Okay, that's just one guess out of the whole room. So you probably will win. You will be the closest. And let's see. Okay, we got 100 something, 99, 106, 100. Okay, so it's not 4 times, it's just 1.5, right? 50%. Why is that? We still just have 2 threads, but 2 JVMs, so 4 threads, right? But there is some kind of additional cost, right? They need to pass the messages between them. They need to have some persistence. We have rebalancing, we have automatic migration. All those things cost. So you need to take that into consideration, right? So we got 100 something, and once again, what we also got is when we kill 1 JVM, we still get the same functionality. The actors are just moved, migrated with the whole state, migrated to the active node. That's how it works. So this is also what we get for almost for free. And yeah, when you are programming, you just don't need to know who is where, which actor resides on which node. When you see it here, this is the line, right? What I just did, I just put a name, sorting the cider name. I don't care whether it's on my node or any other node. And the nodes can join automatically during the execution. And the actors will be rebalanced if there is need for that. Okay, so the project itself is on GitHub, and I created branches for you guys so that you can start whenever you want. For example, just for the sharding purpose, you just check out branch step 3 and just implement sharding. And there is a blog post when it takes you step by step, basically for all the things I just did in 40 minutes, 45. Yes, and thank you very much. And are there any more questions? Yes? Can I have a mic here, over here?
For the actual discovery of new shards and for error recovery, do we get it for free with Akka cluster, or do we need to configure something?
Recover again the discovery.
Well, if some of them fails, like, is it going to handle the error automatically, or we need to do something?
So what you define, that there can be problems with this. Whenever there's, for example, a split brain situation, right? So this needs to be done manually because it cannot be really done automatically. So you need to have some cases that you need to take into consideration. But other than that, when you have just node dropping out, one node dropping out and never appears again, then this is done automatically. So all those actors are persisted in whatever you want, for example, a Cassandra storage or any other storage or distributed data storage. And the actors are recreated automatically on different nodes. So aside from the split brain situation, this all works fine automatically.
And what about adding a new shard? Is it going to be registered automatically? I expect that it's going to happen.
New node, new JVM, when it joins the cluster, what it needs to do, it needs to provide the IP address of whatever node in the cluster. And then it joins the cluster. So yeah, there's no central mechanism. Any other questions? Yeah, over there.
Okay, did you maybe do performance benchmarks with the Akka HTTP module since the early 2.4 versions, because they did a lot of performance work?
Yeah.
Because, sorry to interrupt, because the older Akka HTTP module was doing its work, but the performance wasn't on par with the other solution.
That's really great question, and yes, I did that. And the performance is so good that this talk it cannot be done so nicely anymore, because it really does some nice optimization. So you as a developer don't have to think about as many things as before. And there is a branch in the code which is called Akka HTTP versus spray, and I just rewritten the whole code in Akka HTTP, and all the benchmarks are far better. So yeah. Any more questions? If not, tomorrow at 9 in Mileva, there will be another presentation by me building multiplayer games using streams. So Akka streams, reactive streams. If you don't know what they are, there will be introduction. We'll build the game using some JavaScript and Scala libraries. So if this is not too early for you, 9 o'clock, then please join us. Thank you very much again, and cheers. Have a good day.